A 15 kilogram crate is being pulled leftward by a force of 25 newtons and has a dynamic friction force of 18 newtons. We're going to make a free body diagram of the crate and find the acceleration of the crate. So here we go. We have this force of pulling. Yes, it's 25 newtons, but we're going to use letters. And we have this friction force right here. We have a normal force acting up on the crate and the weight force acting down. So I'm going to actually here work this problem out a little bit faster by skipping just to the part that's relevant. Since we want the acceleration of the crate, I'm going to do what many of you might be doing. I'm going to skip straight to the x direction equation. We do know it's accelerating, which means the forces aren't bound. So I'm simply going to say we have a 25 Newton force being opposed by an 18 Newton friction force, and the effect is that this 15 kilogram crate accelerates. So that's going to give us 7 equals 15 times A, and that will give us A as simply being equal to 0.47 meters per second squared. Next, what is the acceleration of a 680 Newton person who's experiencing a net force of 300 newtons? The net force is 300 newtons. So here's one where we really can't do a free body diagram for it since it's the net force. It's just F net equals ma. This is how you see this equation. Let's be clear that what we really mean by F is sigma F when we write it this way. It's the sum of all the forces acting on the object, and it might even be a vector sum. And all we're saying is that somehow there's 300 newtons resulting on this person that is 68 kilograms, and there's an acceleration. I almost missed that trick there. It's a 680 Newton person. That equals m times g. That's 680 equals m times 10. That's how we're getting that the mass is only 68 newtons. So careful with that little trick right there. That's the weight. Careful. So when we actually get the acceleration of that person, that's going to be 680 divided by, 300 divided by 68, and that's going to be 4.4 meters per second squared. Excellent. Now we want to know the resulting force acting on this. There's exactly 2 forces acting on this crate as shown, and I had no idea what this meant. This is a question that I actually borrowed from Mr. Woodard, and it actually turns out that what's happening is, I don't know, maybe this crate's in outer space, or what's happening is that we are looking at this crate from above. So if this were like a 3D drawing, the normal force would be coming out of the page and the weight would be going into the page like that. So we're only going to look at these forces here. So let's get the resultant force in the x and the y direction. So in the x direction, first let's split this up into its force components. I'll use a different color here. So we'll say that this is Fx, which is going to be 400 times the cosine of 30. Great. And that's going to be 346 newtons. And then in the vertical direction, we'll get Fy. That's going to be 400 times the sine of 30. I'm hoping at this point that if I said 400 sine of 30, you would know that that's 200 newtons because the sine of 30 is a half. So I'm actually going to leave it cryptically like that. And I want you to work out that math. And so the 400 sine of 30 being 200 is something that's actually expected on the AP that you could do that automatically. So if you're, at a 2 or a 3 in mastery, little things like that will push you into the zone of a 4. Now, what is the resultant force acting on it? So let's get the y component. In the y direction, whoops, I don't know what that was. In the y direction, we're going to have Fy plus 200, which is going to give us 400 newtons of force in the y direction because I'm taking this and adding it to that. In the x direction, we're going to end up getting 346 newtons. So here's what I'm going to say. The force vector is going to be 346, 400. So let's actually now get the magnitude of the force using vector components. So that's going to be 346 squared plus 400 squared. Yay. And so we square this plus 400 squared. We'll throw all that under a square root, and we're going to get about 529 newtons. Perfect. Now let's get the angle that the force points at. So theta is going to be the inverse tangent of 400 divided by 346. And when we get the inverse tangent of that, that's going to give us 49 degrees. So our resultant force is going to be, I'm going to write this answer in blue, that's going to be 529 degrees at an angle of 500, let's try this again, 529 newtons at an angle of 49 degrees. And we want to know the acceleration of the crate, so that is going to be F equals ma. Now, in this case, I'm going to actually get the acceleration being at an angle. Let's be clear. What we're basically saying is that the net force is 529 and the angle is 49 degrees. So rather than getting acceleration components, I'm going to get the acceleration as being at an angle. So I can take 529 equals 25 times a. So 529 divided by 25. That gives us an acceleration of 21.2 meters per second squared. And so the way we'll write this full acceleration, that would be enough. But if we want to do this as a vector, the acceleration is going to be 21.2 meters per second squared at an angle of 49 degrees. And at this point, you need to review your rect math if you're not clear on the fact that the acceleration and the force would be at the same angle. So if this sameness of the angles is a mystery to you, you need to review vectors on your own time. All right, so that's the second video, problems 29 through 32, and then we'll finish up in the last video.